Good morning, Australia. URG is very privileged to present global analytics for bridge management. In short, Gabm was designed and evolved specifically for Australian bridge owners who have an inventory of less than 200 bridges. Factually, every single bridge-owning authority must implement bridge management as mandated in Australia under Section 122 of the Local Government Act. The rules explicitly make Level 1 and Level 2 inspections mandatory. It is incumbent on the local authorities to undertake the same. But do they implement bridge management and BMS in the true sense? That brings us to now dwell on my topic, how and why BMS evolved. It is critical that we understand the significance of the word bridge management. BMS was born as a consequence of the knowledge about the budget essential for the upkeep of distressed bridges was insufficient to manage all the bridges. The key objective of any bridge management is the optimization of fund allocation and risk management arising out the same. It is critical to assimilate that bridge management begin post-completion of all levels of inspections. Most micro-inventory owners do not have any funds to implement proper structured bridge management. Many such authorities all over implement BMS manually. They are forced out of the structured BMS fraternity. With the aging of global infrastructure, such authorities also have their share of aging bridges which are bound to show acute distress at the end of design service life. Symptoms alone do not indicate the presence of incremental distress. Location of such incrementing distress are lost in the huge data collected during inspection. Critical here is the correlation of distress and performance. Performance monitoring over a long period is expense. Short-term SHM is the solution. Sustainability is equally critical as a balance between the need to rehabilitate and the economic cost implications must be established. Life Cycle Cost Analysis or LCCA, within the gambit of Finance Department has the solution. Optimization of fund allocation should be flexible and ranking of bridges for fund allocation should account for the importance of technicalities, financial, sustainability and risk from natural hazards. An index should be available for each of these factors which the user can alter based on the ground realities. The level of technical expertise available with such micro-inventory owners is of a level of a graduate engineer. Conventional BMS does not have solutions for all above realities of today. Integrating stand-alone solution under one umbrella is essential. A solution that does not force micro-inventory owners to abandon the implementation. Research was needed to focus on the evolution of a solution that is cost-efficient. URG stepped up in this direction. The aim of the research was to have a solution wherein the cost of implementing BMS per bridge when you have 3,000 bridges or even just 50 bridges to sub $500. Else they will face the same dilemma that authorities faced in early 70s in USA, which resulted in the birth of conventional BMS. Research was aimed to find a solution which addressed the technical needs of today. Namely aging population of bridges which will show incremental distress, need of having sustainable infrastructure, and should be easy to implement technically. Our research got refocused and conceptualization of a cost-effective solution for the global stage has been completed. By early 2023, global analytics for bridge management was evolved. Key factors of Gabm evolved is that it can be internet-free application. It can be operated on any laptop. It is even suited for bridge owners who must implement BMS for only 50 to 250 bridges.
It allows the user to log in using an individual username and password. Once you log into the application, you get an instruction screen which outlines the basic operational intricacies of Gabm. You also have the facility to download the user manual which elaborately outlines the operational aspects of the Gabm. Moving on, one needs to create certain basic data fields applicable for the entire year. These are inputs that are essential for the operational part of the algorithm. It includes basic data related to the departmental budget for the rehabilitation of bridges it owns, average salary of the population, cost of fuel, etc. All data fields are created and used for the year for which they are created. Having created these standard cost data, one can now add bridge data for the level of inspection you must perform in the year for which data has been created. You can now move to the bridge screen. This screen enumerates the list of bridges you have created and has data for all past inspections you performed. The historical data is visible when you press the History button for the bridge you want to view the previous history. You can add iterations for that bridge if the inspection for the same bridge is performed. Alternatively, you add a new bridge. The addition of bridge data begins with Add Bridge button. The addition of bridge data begins with inserting data for bridge identity with basic details of the bridge like its name, road on which the bridge is located, length and width of the bridge, number of spans, and year constructed. The next screen is bridge inspection details, regarding the level of inspection being performed, by whom, when, under what climatic conditions, dates for inspection, data compilation and approval of maintenance authority. Moving ahead, one can enter the details of location of the bridges using simple queries for which the option is either yes or no. This data enables one to understand the impact of location on the bridge's performance. Moving ahead, one needs to input the details of number of lanes on the bridge, the type of road, age, and load capacity of the bridge. This constitutes the bridge classification data. Then, the user is asked to submit details of distress symptoms seen on the bridge with simple queries like type and orientation of cracks seen, existence and severity of the various symptoms commonly seen in bridges like cracks, delamination, spalling, corrosion in rebars, distress near expansion joints or bearing, concrete disintegration, misalignment and bridge components. Finally, information is sought about the presence of severe distress in any single component. Then, input of the various types of elements, their code, and the number available in the bridge is required to be submitted. Each element status is required to be submitted in the form of rating number assigned by the inspector for the element after observation of presence or absence of distress in the element. This data makes it possible for evaluation of bridge structural rating number, BSRN in short. Two options are available for evaluation of BSRN. Either use statistical weighted average rating, or the software can use artificial intelligence program to evaluate the BSRN based on all data provided by the inspector. This completes the official mandatory inspection data input. However, Gabm moves ahead and seeks data about a few more fields to be able to perform and evaluate the results that provide the authorities with satisfaction of having completed the entire gambit of bridge management. The user is required to submit data related to the functional parameters of the bridge like deck geometry, vertical clearance, waterway adequacy and average daily traffic. Most of the data is collected in Level 2 inspection. Then the user must provide details of the socio-economic parameters like the social importance of the bridge, economic growth potential, presence of alternate route, and the environmental impact of the existence of the bridge. Post this, the cause matrix is created using AI tools of the software and exhibited for the confirmation of the user. Details of the bridge, related to financial cost of construction, period of construction is sought before seeking a confirmation from the user regarding the correctness of all data input during the compilation of the bridge inspection report. Once this confirmation is provided, results are generated instantly. Level 1 and Level 2 results are created by the software. Level 2 results include the details of reasons of deterioration and evaluation of balance service life and absolute BSL. The result also indicates the primary reason of distress as per RE.N.1504 document. The financial results in terms of internal rate of returns both for tangible and non-tangible scenarios are presented. When multiple bridges on the network are inspected, the data is compared on the ranking and priority screen for all the inspected bridges in that particular year and fund optimization is displayed. Option to alter the priority based on 3 parameters, namely engineering, financial and sustainability, are also provided to the user. This entire software has been created with the global fraternity of small inventory owners in mind. The cost efficiency is ensured for such micro or small inventory owners also. The cost per bridge irrespective of the inventory size. Further research aims to deliver the modules of risk assessment and management for natural hazards, automated bill of quantity for rehabilitation procedure as per N 1504, incorporation of short-term SHM monitoring of bridges not provided with immediate rehabilitation interventions, uploading and review of 3D models for the entire bridge and photogrammetry models of individual elements showing extreme distress are likely to be incorporated in coming weeks. URG thanks the various authorities and organizations that have made it possible for us to complete this research and development.